Welcome everyone to a very special guest that we've been able to invite to Reykjavík University. His name is Barnaby Wainfan. He has done a variety of amazing things involving engineering of airplanes, air surfaces, and cars. I will read you a little bit what he is, because I can never remember. He's a technical fellow over at Northrop Grumman Airspace. He works as a professor at Department of Aerospace Engineering at University of Michigan, Ann Arbor, and he's a visiting scientist at Caltech. So he's got some accolades. Over his 40-year career, Barnaby has participated in the design of 26 different types of successful aircraft. Take that in mind, 26. He's also active in ground vehicle design, and particularly he's going to talk about that awesome car-looking thing, or maybe it's,
it's
car
there.
thing up there, for the Edison 2 very light car, which won the Progressive Insurance Automotive X Prize. So I hope you give your full attention to him. This should be a very, very interesting talk. Thank you, Barnaby.
Thank you very much. Well, first of all, thank you all for coming, and thank you for the invitation. As Professor Foley said, I have spent my career designing mostly vehicles. And the primary part of that has been aircraft. As you can see, these are all things I have worked on. I started young. But the talk today is more about how to do good design than any specific bit of aircraft technology. I'm going to use aircraft as examples because that's primarily what I've done. But really what I've been doing for my entire career is starting from a requirement and doing the design work to get to a useful machine. Please work. It decided not to. Okay. We'll use alternate means. Okay. Because if you think about it, and design is a discipline within engineering, but an awful lot of what you get taught in engineering really isn't design. Okay. So what's the job of a designer? Your job is to produce a working system, something that actually does something useful for a human. Now, in the real world, in industry certainly, there's also usually another group of people out there designing to the same requirement. So your job is to come up with a system that's better than theirs. So the customers buy yours and not theirs. And so the first step is to figure out, what do we mean by a useful system? Well, useful is defined by what the customer needs, by what the end user of the system needs, not by what the engineer thinks is cool. And that's a trap a lot of us fall into. We fall in love with a technology or an idea, and we forget to think about the end user. What are they going to do? So that's really the first principle that you have to think about, is the goodness of your system is pretty much determined by what the customer wants or needs. Oh, wrong way. And it's fundamentally different than analysis. And a lot of what you get taught in engineering is analysis. And so when you're doing analysis, you want to understand what already exists. Now, for you who are students, what already exists is the right answer to the question on an examination. And your professor knows it, and your job is to reproduce it accurately. And there's one right answer. Design is completely different because you're trying to produce something that has never existed before. And there are a lot of requirements, and there's a lot of goals, and there are a lot of ways of doing it. And sometimes those different ways and those different goals conflict with each other, and the job of the designer is to cut through all that and come up with an approach that will lead to a useful machine. And you give different teams of designers the same job, and they very often come up with very different answers to the same question. So for example, here are 3 different business turboprop airplanes, all driven by the same engines, from 3 different design teams. This is the Beechcraft King Air. This is what another team at Beechcraft designed to replace the King Air. And this is an airplane called the Piaggio Avanti, designed in Italy. Well, these guys got it very wrong. In fact, the Starship was a dismal failure. The King Air continues in production to this day and has still outsold the much more advanced and much cooler Piaggio Avanti. And, you know, if you go back and look at it, it's because it's a very reliable, very effective, very easy to fly airplane. So it meets the customer needs very well. And because it's a simple airplane, it's relatively inexpensive compared to the fancier successors. So in a sense, this is a time when the design teams trying to be advanced missed it. Although the Avanti is still successful in some respects. If I had infinite money to buy an airplane for me, that's the one I'd buy. But I don't. So. And as you set out, the judgment of the designer is really important, and this is what we want to train as we learn how to be designers. Because when you start out, you have very little information. You have a requirement, and you have to figure out where we're going with this. And you're competing against teams that all have the same technology base to work with. Now, occasionally there's a company that has their magic bit of proprietary technology over in a corner. But that's remarkably hard to keep secret. And in large, everybody's got the same technology base to work with. And those decisions you make right near the beginning last for the entire project. And so a lot of the success of the design depends on how good a decision you make near the beginning. And really the key to doing that right is to ask yourself the right question. An awful lot of solving any problem is posing the problem correctly. Because once you have the problem properly defined, then you can do what I will call routine engineering work to solve that problem. There are a whole bunch of things that need to get done after that point. But the correctness of that work in and of itself is not enough, because if you are correctly doing the wrong things, you end up with a whole bunch of useless results. So what you really need to do is define the requirements and the concept of operations of your systems properly. And we'll talk about requirements a little bit more in a moment, but concept of operations is a really important thing that people tend to forget. And concept of operations is how you're going to do the task, as opposed to what is the task that needs to get done. So for example, if I need to get an object from point A to point B, I can put it on a truck if there are roads. I can sling load it with a helicopter if I have a helicopter available. I can put it on a catapult and throw it. There are a lot of solutions, some of which are good and some of which are absurd. So the concept of operations is, which way am I going to do this? So if I choose the catapult, I now have a problem in designing a catapult, and I'm not worrying about trucks anymore, for example. And there are, I wish I had more time, but there are lots of stories, particularly in the history of military airplane design, where they got the concept of operations wrong and they built things that were great flying machines that were militarily useless. So really, early on in the design, you really need to think about how are we going to do this, and then the next question is, what are the technical problems I have to solve to do it this way, in an effective way? And one of the reasons this is so important is this is one of the terribly perverse things about the world of engineering. And that is, as you go down the stages of a project, it gets progressively more expensive to change things. You know, I start out here at the conceptual design phase, I'm drawing pictures. Now, old guys like me still use a pencil. You guys are pushing pixels around on a computer. But fundamentally, if I decide to change something, it's relatively easy to do. I'm paying the time for the person to make the change to the drawing. Now, when I get a little further, like preliminary or detail design, now you're designing something into an envelope that someone else has already created. If they change the envelope, Suddenly, everything you design doesn't fit in the box. That's a lot more expensive. Now, when I get to what we call EMD, which is engineering and manufacturing development, now I'm building parts, I'm building tooling, I'm building hardware. Now it gets really expensive to change things. And if you get to the point where you're in production and you have to go back and change, it's incredibly expensive. The Boeing 737 MAX problem right now is an example of that. I mean, you have to ground a whole lot of airplanes, go back, fix them, recertify them, and the cost is enormous. So there's a huge benefit in getting it right early. However, at the same time, how well you understand your system is getting better as you go along. So the hard part is right here where it's cheap to change things, you don't know a whole lot. And this is why getting your judgment calibrated early in the design process is so important. Because if you get things right here, you don't end up with the big problem there. And once again, the MAX is a really interesting case there, because there was one decision made very early in the structure of this flight control system that if it had been made the other way, they never would have had the problem. So at the beginning, since you don't have a lot of data, you have to make some assumptions. You have to assume certain things. Once again, judgment is important because you don't have much information. And you have to do it, but you have to be very, very careful. Because a lot of times the assumption creates the answer without you realizing it. And it can rule out winning ideas because you just assume it doesn't work that way, or you assume a way to do it. And sometimes people make assumptions based on emotions. I just like airplanes with V-tails, for example. Well, I don't, but some people do. So even though you need to make assumptions to start with, there are things that you should treat suspiciously as you go along. You know, if there's something that's constraining what you're doing, and it's an assumption you made at the beginning, periodically examine those. Because what you're trying to do is understand what you're doing. And once again, getting these stages of understanding is very important. You know, and this is getting more and more as we have better and better sensors and more computers and more ability to get information, we are more and more in danger of getting buried under a pile of data that we don't know what it means. Because data in and of itself provides no knowledge. It's just a bunch of numbers or measurements. Once you get it organized in a meaningful way, now you have some knowledge. So now, for example, if it's an airplane, I know how much it weighs, I know how fast it goes, I know how far it will fly. The next step is starting to understand that at a system level, so it tells you how that system functions well enough to be able to move beyond the data, to come up with the next idea or synthesize a new idea. And that's called insight, and that is really critically important. And the more insight you can develop as a designer sooner, the better your designs will be. So always, when you get a result, one of the questions you should be asking yourself is, what does this mean beyond it weighs 500 kilos? What does that mean? What does it mean in terms of the performance of the system? Where can I do better? Things like that. Because we're trying to meet a set of requirements, always. You know, in the commercial world, very often the requirements are set internally. In the world I live in, the requirements come from outside mostly. And once again, a true requirement is something the system must do in order to be acceptable. And then you have constraints, which are things it can't do or can't be bigger than, so it's the box you get to work in. Sometimes those are physical, sometimes those are regulatory. But the thing is, a constraint is something where you can have a system that meets all requirements, but if it comes outside one of those boxes, it's not acceptable. Then you have things that are goals or things that are nice to have. This is a trap engineers fall into a lot, particularly young ones, because they typically want to give you more and more and more of the nice-to-have thing. So for example, and in some areas you can actually sell this, for example, with cars, how fast the top speed of a normal road car is really a meaningless number, right? You're not legally allowed to use it. So making a road car faster may be of no benefit whatsoever, but it feels really cool to the engineers. So you really need to keep track of which are important. You know, and it's one way you see things packaged a lot in requests for proposals is you have what they call a threshold and then a goal. The threshold is the minimum performance the customer will accept. The goal is where they'd like to get, but the thing to keep important is anything above that, they don't care. And as a matter of fact, it tends to work against you because it tends to make things more expensive. One of the things about design that takes a lot of learning is every bit of performance above the requirement that you put into a system costs money. That makes your system more expensive. That means that your competitor who is doing the just barely meets requirement system will probably beat you on cost. Requirements, there's a lot to unpack with this. I won't go into it in detail. But the thing to understand is there are requirements that come from outside and there are requirements you place on yourself. And once again, you need to keep track of which is which. So let's say I'm building a bridge. I have a requirement that it be able to carry this much load, these kinds of trucks, these kinds of cars. Well, I may say that means I need to use this alloy of steel in the structure and make that a requirement to my design team. Well, that may not be the only answer. So I need to really be careful about that. That the absolute requirement for the bridge to carry the load is there. It's never going to go away. But that steel, maybe not. Maybe I can use concrete, maybe I can do something different. And that's called a derived requirement. A lot of times they're important, but they're different than the absolute requirements are the primary ones, and you really have to pay attention. Because I've seen situations where a derived requirement turns out to be wrong or not a true requirement and ends up severely constraining the design. So as we go down the design, we're making decisions. So the first thing is, I use the word mission. It's as similar as function. A lot of this comes from the airplane world. So your design decisions have to be based on how well your system does what it's designed to do. And you always let the requirement design the configuration of your system, not the other way around. This is a very common problem in the vehicle world, that people fall in love with a design concept and they try to force the design concept to do the mission. This is particularly true with advanced airplanes. You know, the people, if you look in the airplane world, about every 10 years, there's a magic configuration that's going to be better than everything that's ever been done before and solve all our problems. Well, it may over here, but if what I'm doing over there doesn't fit it, it's useless. It's also very easy, as I said, what we call requirements creep, to start adding capability. You say, okay, I've got a 2-seat car. Well, we could use a back seat. Sometimes we have to take something. And while we're at it, a trunk, and maybe a roof rack, and maybe some off-road capability. And you know, you start out with an economy car and you end up with a truck. And that's a way of adding a lot of cost. So you really need to keep a sharp eye on the customer requirements. And once again, and you're going to hear this from me many, many times, the success of the system depends on the designer making the right design decisions at the right time. And so an example of how important it is to understand customer requirements, this is a really cool one in my mind from the history of airliner development. If you go back to about the year 2000, Airbus was working on the A380 airplane, and there was great consternation in the United States that the Europeans had stolen the march on the Americans because the A380 was actually going to be bigger than the version of the 747 that Boeing was working on at the same time, called the 747-800 at that time. And if you read in the press, it was, oh dear, we've lost the lead in airliners. The Europeans are building a bigger airplane than ours. Oh, this is terrible. And then Boeing apparently surrendered. They canceled the 747-800. And people started sounding even more upset. Not only are they beating us, we've surrendered. And then Boeing rolled out this airplane, or models of this airplane, which they were calling the Sonic Cruiser. The idea was, okay, we're not competing with Airbus on the biggest airplane in the world anymore. We're going to do this, and it's going to be even cooler. And the idea, I mean, I'm not going to read you this quote, but you can read it from here, is that they were going to produce a revolutionary new type of airliner. They were going to use advances in aerodynamics, composite structure, better engines to produce an airplane that could fly just under the speed of sound, Mach 0.98, so that you didn't have to worry about sonic boom and the noise issues for supersonic transports, but you would still be about 20% faster than existing airliners, and the combination of the advanced aerodynamics and the advanced engines meant that it was still going to burn 10% less fuel per passenger mile than the 767. Well, this sounds pretty cool. And Boeing went out and started trying to sell this. I mean, look, you're going to be faster, you're going to burn less gas, you're going to fly 10,000 feet above all the other traffic so you can go direct. This is wonderful, right? Well, they went out to sell the airlines. You notice how many of these you see on the airport now. Well, what happened is, as they were out going to selling to the airlines, because one of the things about giving a presentation on a design is you want to anticipate the questions that someone's going to ask you. And so you knew, if you're Boeing, that some airline was going to say, okay, well, what if you put this conventional technology on a conventional airplane, this advanced technology, on a conventional airplane? So in parallel to the Sonic Cruiser, Boeing had designed such an airplane strictly to be the airplane that would contrast badly with the Sonic Cruiser. So they showed, okay, look guys, if we put all of this marvelous technology in a conventional airplane, it doesn't fly any higher, and it's not any faster, and it doesn't look any cooler. It does burn a little less gas than the Sonic Cruiser. It's 20% fuel savings instead of 10, but it's not faster, and it's not. And the airlines all said, I can't sell speed, man, but if you can save me another 10% of fuel, I'm all over it. And guess what? So in the end, what happened is this airplane was originally specifically designed to look bad next to the Sonic Cruiser. But what happened is, in the process of marketing this, Boeing got the airlines to reveal to them what they, the customer, really cared about. And what the customers really cared about was the cost of the fuel they burned. So the origin of the 787 was an airplane that was never supposed to be built. It was just supposed to be look bad for the one that the engineers thought was cool. But Boeing was smart enough to listen to their customer, and when their customer said, we don't care about being faster, but we care more about fuel, they proceeded to build the 787, and if you look historically, it was an amazingly good decision for them. Because it turned out that the model, the business model for the extra large airplane was breaking down. The A380, if you look at it, was a financial disaster for Airbus, because the fundamental assumption that was built into it, which that all major airline operations would be hub and spoke, and that the airports were simply running out of flight slots, you could only bring one airplane in and out every 45 seconds, was going to limit the number of people you could take through the hub unless you built bigger airplanes. Well, what Boeing did eventually is to say, well, how about if we build a more efficient, smaller airplane and fly point to point? So the 787, in addition to being so efficient, also allowed the airlines to change their basic concept of operations. And the net result is Airbus has announced the end of the A380 program, having lost an enormous amount of money on it. And Boeing, in spite of their problems getting the 787 to work initially, is still building these, still selling these, and will probably be doing so for decades. There's another, so that's one piece. There's another critical piece to being a good designer. And that is a real understanding of the fundamental principles, the physics that control your system. There's this marvelous old saying that says, inside every complicated problem, there's a simple problem hiding and trying to get out. And a good designer can find that simple problem that's hiding under the complicated problem. And this is particularly an issue in the design of modern systems because they are very complex. And it's very easy to believe that the complexity makes it almost impossible to do purposeful design, that what you have to do is basically do simulations upon simulations upon simulations, or use optimizers and let the answer reveal itself. But usually, in most problems, there's a very small number of those variables that have a big effect on the effect of the performance of the system. And the rest are details. Now, that doesn't mean you can't really mess up a system by getting the details wrong. But in terms of the system architecture, if you can dig down to understand what those few fundamental variables that control it are, then you're able to make big changes in how things work, and you're able to drive the design in a purposeful way. Now, once you do that, you have a lot of interesting options. Once you have that understanding, because that lets you to decide how radical a design you want to do. It lets you decide whether you want to stick with conventional practice and refine it, or whether that fundamental understanding lets you go to a completely different system architecture. So it's very important to understand that. Now, here's an example. Here's when I learned this. This is a long time ago now. When I was in my teens, I used to compete in an event called Control Line Combat with model airplanes. And these are model airplanes that are flown on the ends of wires. And the pilot has actually control of the elevator with a handle. You have two wires and a bell crank in the model. And for sheer craziness, what you do to compete is you have two people flying in the same circle. So you're standing next to each other. You each got your model out there on a string, trailing a paper streamer and trying to cut the other person's streamer with your propeller. And it's crazy. I mean, you're all over the place. When I started flying competition, I grew up in New York City, and it turns out that the US national champion in this event flew at the park I flew, and there were various other people who were at that same level. And so, needless to say, when I came out with my first few airplanes there, I didn't do very well. I was very inexperienced. I was flying against championship level people. And I was getting slowly better, but I'm impatient. Even now I'm impatient. You want to see what I was back then. And so I decided that I would concentrate on developing a better airplane. Because the way to beat someone with superior skill is to have a superior weapon. Well, I started thinking about it, and everybody else was designing their airplanes to be as fast as possible, with the idea that you'd run away from the guy chasing you. Well, I figured out that there's no place to run. The airplanes are on end of strings. There's this 60-foot radius hemisphere, and you're going to be somewhere on that hemisphere. So I started designing my airplanes to turn better. I put bigger wings on, made my wings thicker, so, somebody's chasing me, I'll just go over here. I don't have to chase him, I can just maneuver around and wait for him to come around. So I did that. And what happened was fascinating, because when I first brought my new airplane out there, they laughed at me. One of my favorite moments in this competition was the first contest I ever flew with this new airplane. One of the kind of upper mid-level people who was not a nice person spent 20 minutes telling me why my airplane was dumb and I was stupid. And then I drew him in the first match. I changed his mind in about 15 seconds. I beat him quite soundly, and then went on. I actually made it to the finals in that contest. I never won a contest with these airplanes. The other guys I was against were too good. But my superior airplane got me from the bottom of the pack to routinely making it to the semifinals and the finals. And that lasted about 2 years. Because in the first year, it was, who is this silly person with this dumb airplane? And the second year is, hey, he's getting competitive. And then they realized that I wasn't that good and it must be the airplane. And they started copying the airplane. And then I fell back down the pyramid to where my skill had me. But I had my moment, and it was a really good example of how, really understanding what's important can drive you to a superior design. And then I actually put a few more innovations in my next generation airplanes, which I'm very proud to say are now completely illegal because they worked so well that the sanctioning organization felt it was necessary to outlaw them, which is the highest compliment any sanctioning organization can pay an engineer. Is if you're designing something that works so well that they feel that they must outlaw it. You got it right. But, this highlights a question, and once again, this is partially for the young people here. There is this enormous push to be doing things that are advanced and innovative. You hear those words all the time. But please remember that conventional practice is not conventional because the old people are stupid. It is conventional because it works. Nothing becomes conventional if it doesn't work. And very often, a very simple, straightforward design is the right answer to the problem you have. Now, sometimes you can add new technology to an otherwise conventional design and improve it. The 787 is a good example. That airplane doesn't look that different than airplanes that are 50 years older, but there's an enormous improvement in efficiency coming from evolving that conventional design with advanced technology. Sometimes advanced technology enables a new concept. Sometimes there are things that you've always said, yes, it would be good to do this, but I don't know how, or it's not possible now. And then somebody invents something that lets you do it. One of the things that's fascinating to me, I'm in the airplane world once again, is I read a paper written by Jack Northrop, the original creator of the flying wing, in 1946, where he describes in detail all the performance advantages you could get with a fully digital autopilot system like we have in modern airplanes. Now, he didn't call it that. He called it a sufficiently fast responding autopilot. He understood it in detail, he just didn't have the technology to do it. So this is the other interesting thing as an engineer, and this is why one needs to look beyond your own field. Because sometimes someone over there will invent something that lets you do the thing you always wanted to do the advanced thing that was not possible with the technology you had available. And the thing about getting too radical, too innovative, is sometimes it produces a breakthrough. But it's always riskier than doing a conventional design. So very often the choice is between doing a good conventional design that works and what is the real benefit if I take the risk to do a more advanced or innovative system. And that's a very tough choice. Because the answer is sometimes this, sometimes that, and sometimes they both work, who has a better marketing department. But every now and then you end up with a problem where a conventional design can't do what is asked. And then you have to get back to this idea of what's really driving this problem. What kind of radical architecture can I do? Is this even possible? And this is a project that I was involved in, which was exactly that. In 2010, the X Prize Foundation offered a prize of $10 million. It was actually 3 prizes, $5 million, $2 million, $2 million, 2.5 and 2.5 for 3 classes of car. But what they asked you to create was a production-capable car with a fuel economy of 100 miles per gallon equivalent or better. And by production-capable, they meant it had to be drivable on the normal highways. It had to meet emission standards. Actually, it had to meet the upcoming 2014 emission standards. It had to be theoretically possible to meet all of the safety and crash requirements. So it couldn't be just a paper-thin mileage thing run just on a track. And this is some of the details. A lot of people tried. 115 teams entered, 136 vehicle designs. The committee, the X-Prize committee, looked at everybody's submissions and decided 46 teams' design was realistic enough that they were willing to at least let them try. You had to do 4 rounds of trials, real driving on real tracks, and the winner was announced in September of 2010. And I'm very proud to say that that car I just showed you was the car that won the prize. But look at the challenge that they hit us with. They wanted us to increase fuel economy by a factor of 2 times the best production car that you could buy at the time. Because the 2007 Toyota Prius, according to the United States EPA, got 50 miles to the gallon. The X-Prize Foundation wanted 100. And by the way, there was no prize for 99.9. The way that the prize was, the contest was structured, you got 4 rounds of trials, and in the end, the cars that met the requirements, the 100 miles per gallon in the knockout round, had to race to see who would win, because the prize in each class was for the car that went around the course fastest while staying within the mileage limit. Now that was very easy for our team in our class, because by the time we got to the finals, our 2 cars were racing against each other because no one else made it, which is a good place to be. But here's the thing. I designed this car with a lovely gentleman named Ron Mathis, a good friend, one of the most brilliant mechanical engineers who's ever walked this planet. He spent his career doing race cars. And Ron and I started looking at this problem, and we realized almost immediately that everyone else was looking in the wrong direction. Because everyone else was looking at making the powertrain more efficient and putting it in an otherwise conventional car. They were talking about hybrids and electrics and turbo diesels and all of that. And we looked at it and said, well, first of all, this is very difficult because an awful lot of very smart people have been working to optimize powertrains of automobiles for a very long time, and they're good at it. So you're getting up to the diminishing returns. You're getting up to the asymptote there. We looked and said there's not another factor of 2 available from the drivetrain. So what's the really critical thing I care about? How much power does it take to make this car go down the road? Because the less power I need, the less fuel I'm going to burn no matter how I'm generating the energy. Then if I get the drivetrain right, maybe I can make it. So that was the critical insight, and that's what set our design architecture, and that's the direction we went, which was very different than almost all of the other competitors. So now we get back to physics. What really matters here? Well, what determines the fuel consumption of a car? I have to accelerate it up to speed, and then I have to keep it rolling down the road at constant speed. Well, acceleration is strictly a function of mass. How much does it cost in energy, right? For F equals ma. I've got to put a certain amount of kinetic energy into this mass. That's not much I can do about that. Now, resistance as I'm rolling is a factor of 2 things. It turns out that the actual rolling resistance of the car is also a function of the weight, because it's basically whatever your coefficient of friction of the tires is. And then the other piece is aerodynamic drag. So what it really got down to is, once again, thousands of variables, only two things matter. How much does it weigh and how much drag does it make? Now how you do that, that's a big engineering task, but that's the fundamental insight. Well, here's what we ended up with. This car has a steel tube frame with a composite body. It's a full 4-seat automobile. But to keep the drag down, what I realized as an aero person is we couldn't afford the base drag, the flat drag of the flat back end of most cars. You know, most cars have a chopped off back end and then there's an area of dead air behind it, which means we needed a streamlined body. In order to do that, I've got to let the air go between the wheels and the cabin, which is why you end up with this configuration that looks like an open wheel race car except with fairings over the wheels. Now we get to details. One of the high drag things on a very clean car, or if you look at a Formula Racer or something like that, is the suspension, right? Because that's out in the air. So I went to Ron and said, Ron, we can't afford the drag of suspension that's out in the air. And that man invented two never before done suspension systems that fit entirely within the hubs of the wheels. The rear was relatively easy. It was just a trailing arm. But he tucked inside the hub of the wheel a AA arm suspension with a shock absorber that hangs off the steering spindle, weighs about 8 ounces, and produces all of the suspension travel and geometry of a conventional suspension. You think I'm good with aero? Ron with mechanical is just a wizard. That car would pull over 1G lateral on the skid pad with no aerodynamic downforce. Okay. GM got wind of what we were doing, and for the first time in history, they gave someone a free session in their wind tunnel. So we got to go test in the GM full-scale wind tunnel in Warren, Michigan. And these are the actual numbers we got.
What about cooling?
See those nice little holes right there? The air sees it just enough. Cooling was a real bear, but we just barely got enough air to go. It's a rear-engine car. We just barely got enough air to go in those little NACA ducts.
It was rear-wheel drive as well?
Yes, rear engine, rear wheel drive. And that was very marginal. After the contest, we figured out something even cooler to make it cool better. But we got it. We managed to not melt on the track, which is what counts. To put this in perspective for those of you who don't speak drag coefficient, these vertical bars represent the total aerodynamic drag of a variety of cars. So here's our car. Here's a Toyota Prius. And here's the not-so-smart car. When we turned on the air, and by the way, just have to brag about this for a moment, that's real smoke. That's not photoshopped. I was standing about where you are when this picture was taken with, you know, I probably had more drag than the car. And I'm standing there trying to not get blown downwind, but you know. So basically we achieved what we set out to do in that the aerodynamic drag was less than half of the production car. Because of the lightweight and Ron's brilliant chassis, the rolling resistance was less. And these are the numbers we actually got on the track. And keep in mind, this is not a hybrid. This is not an electric. It's an internal combustion engine driving rear-wheel drive through a 6-speed sequential gearbox. Now, we did some interesting things in the motor, too. We were running E85 because you can get away with ridiculous amounts of compression. We did a lot of cool things on the motor, but fundamentally, it was getting the total amount of power required down that made this work. And this is one of my favorite pictures to show just how little energy this car took to move. Because as you see here, Peter is pushing the car out with his thumb. And our driver's already aboard. And that's one of the ways we knew we were probably going to win this thing, is we got out there and we were pushing the car out to do a run, and PK is like this. Peter's last name was Casimir, we called him PK. Right? And the other guys were towing their cars out with ATVs or 6 people pushing or whatever. This car is amazing. You just reach up, touch it with your finger, and it would just start to roll. So the real key here to energy efficiency wasn't the drivetrain, even though we did some trick things on it. Just to give you an idea, we took one of our spare chassis after the contest, and we took the drivetrain out of a smart car and dropped it in cold. Driving on ordinary pump gasoline, we didn't even change the transmission ratios, and our team owner drove that car for a year as his personal driver and averaged 98 miles per gallon over an entire year of normal operations. So we know it works. Now this is one of my little escapades. This is an airplane that I built in the early 1990s and flew and survived. And this is an example of exploring a completely different architecture of aircraft. And it comes out of contemplating, in a sense, what's the real job of any vehicle, but in this case, particularly airplanes. I want to transport a piece of payload from here to there. So what does the customer, the operator, care about? They care about how much it costs to move that payload from here to there. How much fuel do I have to burn, basically? They don't really care that I'm efficiently transporting the vehicle from here to there. And so when I look at it, it's easy to start looking at it in a single discipline way, right? We're all specialists, so we tend to be. So the aero person looks at the lift to drag ratio, which is the aerodynamic efficiency. And the structures person wants to make it light, and aero blames everything on propulsion, but the engine people are trying to make the engine most efficient. All sounds good. But what I really care about is at the system level, not each one of these individual components. Each one of these individual components only has value in that it contributes to the overall efficiency of the system. So what I really care about is not the lift to drag ratio, but the payload to drag ratio. How many pounds of drag do I generate? How many pounds of thrust do I need to generate to move a pound of useful load, payload, through the sky? The airplane can come along for the ride. So, if you do the math, and I won't trouble you by going all the way through it, what you discover, and this is one of those beautifully simple formulations that gets you buried under out from under a complex problem, that the payload to drag ratio is just the lift to drag ratio, which is essentially the aerodynamic efficiency of the airframe, times the ratio of the payload to the actual takeoff gross weight, which is the structural efficiency of the system. Now you can trade the two directly, or mix the two together directly. And that leads to some very interesting results. Because I've said most of this already, but the standard approach is each specialist tries to optimize his bit. You put it all together. If each specialist has done a good job, you end up with an airplane that was somewhat better than the last one. However, now, there's a big push in what we call multidisciplinary design optimization. This is sort of a simple example of that what we're really doing here is trading explicitly, is it better from where I'm at now to make the structure lighter or make it more aerodynamically efficient? What if I let it be less efficient aerodynamically, but much lighter? Or the other way around. And you end up with very different architectures. Now, what's interesting is this is not original to me by any means. Some people were doing some very cogent thinking about this a long time ago. So here's something from the early 1960s. Believe it or not, this design is actually the ancestor of all of Airbus aircraft. This was a design by a gentleman named G.H. Lee for what he called an OG Aerobus. But the basic idea, what he was studying at a British aircraft company called Handley Page Aircraft, was a short-haul airliner, 400, 500-mile stages. And HP was actually thought a flying wing was a good approach, so they designed a flying wing airplane, and they did all their analysis, and it wasn't any better than the conventional airplane. And this bothered Mr. Lee enough that he went and did some very beautiful, detailed analysis, and what he discovered was their flying wing design had too much wing. because a lot of the wing didn't have anything in it. It was a low-density aircraft. So he said, fine, what if I just cut the outer wing panels off? And when he cut the outer wing panels off of his design and reanalyzed it, it got better. So he said, well, it's kind of ugly with just stumps there, so how about if we smooth it out and make it pretty? And you end up with what really looks like if Fisher-Price made a Concorde. But he actually published, and this paper is really worth reading, because there's a beautifully cogent mathematical analysis of how this shape ends up being significantly better overall at a system level than a conventional airplane. And he actually has, I believe, a sketchy design for something that looks like a DC-9 or an MD-80 to compare to. Now, unfortunately, shortly after this paper was published, a Handley Page aircraft went bankrupt. And so this concept never got past wind tunnel testing. But it's a really good paper for illustrating this concept of thinking in multi-dimensions at a time before people just hit you with 17 partial differential equations and said, we simulated this numerically in the computer and here's the answer. Because this was done at a time when the calculations were being done with a slide rule. So the one advantage of having primitive analysis techniques available to you is you really need to understand the problem, because you can't just hit it with a bigger hammer of more analysis. So I had read this paper and many other things, and my first love is really personal aircraft. So I wanted to go explore taking this concept and moving it into the personal aircraft world. And so that's why I built this airplane. And there was history, once again, that had cued me somewhat. And once again, for those of you who are going into design, one thing I can't say enough to aspiring engineers and designers is read history. Read what's been done. An awful lot of people have done an awful lot of interesting things. And what I find particularly fascinating is when you find an anomaly. You look at that airplane, for example, one of my all-time favorites. But conventional wisdom would say that is an aerodynamically inefficient airplane. It shouldn't work for a long-range bomber. But it did, and it worked really well. Well, a good engineer looks at that and goes, why? What did they understand? What did they figure out that I need to know? And then the other concept that mixes into this, and once again, Lee was way ahead of me, is the idea that Jack Northrop also advocated, that every part of an airplane should make lift, that anything that isn't making lift is simply along for the ride. Now, of course, as we've shown with this conventional commercial airliner, sometimes that actually works pretty well. But all lifting configurations are also something that have considerable value. And I had the great good fortune during my career at Northrop to get to design this airplane, which in a sense is a descendant of my little airplane, because I did this 10 years later. But when you packaged it all up, this configuration had a lot of advantages for, once again, looking at customer requirements. What does somebody flying a personal airplane need? They want it to be inexpensive, they want it to be safe, they want it to have pretty decent performance, and this looked like it would do it. So I built it. Here's the interesting thing now. Once again, go do statistical analysis. If you look at weights, this is that useful load fraction, payload over gross weight. These are all the all-lifting, low aspect ratio airplanes. These are all the conventional airplanes. So there's this big benefit there. So now the question is, can I get that benefit and not pay too much in the aerodynamics to have it overcome it? And I'm not going to go through this in any detail, but the answer is yes. So when you take, and in the end, that airplane, that whole airplane sitting on the ramp weighed 370 pounds.
It's 150 kilos?
About 150 kilos. It would carry its own empty weight and useful load, and it would cruise at right around 100 miles per hour on 46 horsepower. So it kind of worked.
So what are the disadvantages?
Say again?
What are the disadvantages?
What are the disadvantages? It's very difficult to get the structure acreage light enough. And it's also a royal pain to get in and out of. The door is in the floor. Well, because you walk up to the airplane and you're 7 feet from the cockpit, and it's so light that if I put a step on the side of it, it would tip over. So I guess the other thing to look at is whenever you get to a completely different concept, there's a whole lot of things you have to figure out when there isn't conventional practice already in place. So the sheer number of hours that goes into designing it the first time is much larger. But once you've got it figured out, you can do good things with it from there. So just to compare this airplane from a transport efficiency viewpoint to a conventional airplane, and as it happens, I also own one of these. It's very interesting because if I look at it aerodynamically, this is lift to drag ratio as a function of airspeed. There's the Cessna, and there's my little airplane. You know, the aero guy would tell you, this thing doesn't work very well. When you look at transport efficiency, actual fuel burn or horsepower per pound mile, I get out in the speed where we're cruising and the curves actually cross. My airplane comes out a little bit ahead. Now, I learned enough from building this one to know that I'd gone a little too far in reducing structure weight. I went down to aspect ratio 1. Turns out that the real optimum point is somewhere around 1.6 or 1.7. I am busily designing structure for that airplane right now because I think I can get about a 50% improvement over where we were. And it's definitely something I want to fly. It's just too much fun. So, you know, this whole idea of how do we package things together to do a mission more effectively, I mean, I'm still working on all kinds of interesting things. And one of those is this vehicle. This is a drone airplane for delivering supplies. The company that I'm part of is called Corvid Air. And the scenario in particular we were thinking about was a rescue team kind of scenario where you have somebody out in the wilderness, injured, unable to extricate themselves, and you need to get first responders to them, and those people need equipment. They need supplies, and it's a difficult place to get to. Well, you know, you can fly them in on a helicopter, the first responders in on a helicopter, maybe, if the weather is good enough and if a helicopter is available. And if not, then they have to pack in all that equipment themselves. So the thought is, what if we could take some of these concepts I've just been talking about and build an autonomous aircraft that can take the critical supplies up to that site, the rescue site, so that the people going in can travel light. And if they then need something once they get there that they don't have, they can call back to base and have the vehicle, the drone, bring them more stuff. And you can supply in place. And so what we've done is take some of these same concepts of payload efficiency and transport, and also what we can now do with autonomous control to allow us to precision drop that payload. This is actually a picture of one of the very first drops we did. You can see the vehicle flying overhead and the payload coming out. The aircraft was about 3 meters above the ground when we released the payload. This is being flown manually. Just to give you an idea, this is the operator. He was trying to drop the payload in front of himself. You can see how well he did. We're working now on autonomous control, and we believe we will be able to be about 1 meter above the ground when we release the payload. And because this vehicle can fly quite slowly, or vehicles like this, one of the advantages of this low aspect ratio approach is that it's got lots of wing area. So it can fly at high angle of attack and get very slow. So we'll be able to be maybe 1 meter above the ground going maybe 30 miles an hour and release the payload. And at that point, we could probably put it in something the size of a kid's swimming pool consistently. And so that work is ongoing. These vehicles are still flying. The next generation is under construction. It's a very exciting project. And once again, it's very cool to be able to take things that I've learned over a very long career and grab some of this new enabling technology and bake it into something that can do good things and keep going. And that's the other thought I will leave you with, is that design, this act of creating new and useful things, is a wonderful way to spend your life. It's a great way to make a living. I've been doing it for 40 years. I'm not done. I'm not even close to done. And I'm still truly enjoying myself. So with that, that's the end of what I have prepared. Thank you very much for your attention. And I will be glad to answer questions for as long as all of us can stand it. Anybody? Yes, sir.
You haven't mentioned electrical aircraft.
I have not mentioned electrical aircraft. No, I have not. I remain unconvinced. I think a lot of what is being done with electric aircraft is a case of people being enamored of the technology without quite understanding how it fits into the mission. And in particular, there's obviously a driving other motivation to go electric. In other words, there's this huge environmental interest in the idea of having the aircraft itself not emit. Now, the next step is, okay, where's the energy coming from? Because if I'm still generating it by burning fossil fuels somewhere else, maybe that whole energy cycle may not be as clean as people think. One of the things about electrics that's very interesting is it lets you do things you can't do with a normal system, because I can distribute the motors in various places. So I can start doing interesting things with distributed propulsion and flow control and high lift. So there's some exciting possibilities there, and we're still at the very early stages of understanding what it means. It's very clear that you need significant advances in battery technology before we can get to it being really useful for long-range aircraft. There are electric trainer aircraft flying now that work very well. So in some respects, it gets back to that payload to drag empty weight fraction piece of the equation. That is, right now the batteries are very heavy, even the best ones. So that's really the place that you want to focus if that's going to become a useful reality. Yes, sir.
Do you have the information about the suspension system?
Do I have the information about the suspension system?
See it, because you just said it was awesome.
Well, actually, it is patented.
Oh.
So, no, the good news is, remember, what does the word patent really? It is a patent disclosure. And what that means is, in return for putting drawings out that anyone can duplicate, the government provides you with 17 years of commercial protection. So what you want to do is go into the United States Patent Database and search under inventor's name Mathis, M-A-T-H-I-S. First name R, Ron, or Ronald, I don't know which he put it under. And there is a patent out there with beautifully drawn drawings showing exactly how he did it. Yes. Yeah, I mean, that's the interesting thing about patents, is patents were not invented because governments liked inventors. Patents were invented because governments were afraid that inventors would hold their secrets so tightly for commercial reasons that the knowledge would be lost if the inventor died without succeeding in business. And so that's why the idea of a patent disclosure, that if you put drawings on public record so that the invention is not lost, then the government would protect your commercial interests so you didn't have to keep it a secret.
Did you try to Did the car produce any downforce, or were you just using?
Did we try to make the car produce any downforce? No, actually, absolutely not. Because that's a classic example of adding something I don't need.
Yeah, so it's just efficiency.
Well, you remember, I'm not racing on a circle track. The whole purpose of putting downforce on a car is to corner better. You pay aerodynamic drag for that downforce. The car actually generated a little bit of lift, so and later on we would have probably put a little bit of rake in it to take that lift off. But downforce costs drag. On a normal highway, particularly given the way this car already cornered, we didn't need it. It would have just hurt.
How heavy was it?
What, the car?
Yep.
360 kilos on the ramp. Yeah.
How was the braking?
It met all of the safety requirements. Actually, we had to do several things. I mean, it was basically a very fun car to drive. It drove like a monster go-kart. You know, because it had this wide stance, it was very light, it was very responsive. One of the trials you had to pass was the American Automobile Association has a safety check, it's Consumers Union, I think, where it's at 45 miles an hour, it's a double lane change, where you have to come in, sidestep a lane, and then sidestep back around two obstacles. And the rules are that you're not allowed to touch the accelerator or the brakes during it. You have to hit that and then do it all with steering wheel input, so you can't drift it around. And we had to do that at 45 miles an hour. And we passed that test. As a matter of fact, we were the fastest through that course of any of the teams. If you want to see a truly hilarious video, if it's still out on YouTube, there's a video of the Aptera car trying to do that, you know, which was a three-wheel electric. And halfway through the spin out, the passenger door pops open. They eventually managed, but it took them about 15 tries to get one run at 45, where they just barely did it. We did it, I think, 48 or 49.
Is it the same as the used?
As the what?
Have you seen people, the Toyota Hilux doing a similar thing and almost rolling over?
No, I haven't, but I think it's the same test. And, you know, it's a test of suspension dynamics and other things. This car actually was, you know, really well designed for that, almost by accident. Because one of the things that we had to do, in order to have the channels for the air to flow around the cabin, we had to go very wide on the chassis. I mean, we kept it within what was out there in normal road vehicles, but we had the, you know, the tread width of a big sport utility vehicle, not an economy car.
Did they make you crash it?
They did not make us crash it. They made us prove it by analysis, or allege it by analysis. Analysis is never proof of anything. And by the way, that's another thing for young engineers to remember. Until you do the actual experiment, it's an educated guess. But in fact, what we did afterward is, since we built up several spare chassis, is we actually did take them to the Insurance Institute and crash several of them, and they didn't meet the requirements.
Cool. Also, it looked pointy, which might make it dangerous for the things it crashes into.
Well, it isn't pointy per se. It's somewhat blunt. Now, that car, as built, because the requirements did not require it, does not meet the current bumper requirements, obviously. And I think it meets the pedestrian safety requirements, but it's marginal. It's not really pointy, it's blunt. But there are small changes that could be made there. And as a matter of fact, unfortunately, the company, which was called Edison 2, is no longer in business. But their website is still out there, and if you go look, there are drawings of the next generation car, which got as far as a rolling chassis, but never went beyond that. And in fact, we were addressing these things. Once again, in the nature of reading the requirements very carefully, these cars were tailored specifically to the requirements of the prize. Yes?
Did you come up with anything that was banned?
Did I come up with anything that was banned? Not on that one. I tried. But no, we skated on the edge of the rules in a couple of places. For example, there was a requirement that they hit us with very late that the cabin temperature stay below a certain temperature for the entire run. And we're going, wait a minute, it's Michigan in July. Why didn't you tell us this before? right? So what we did is the trunk was in the front. So we put a cooler in the trunk and filled it with ice and ran a tube from the cooler into the cockpit with a little fan to blow the air into the cockpit. So we managed to keep, it's a great air conditioner for about 20 minutes, but we only needed 15 to do the run. So we met the rules. But, if you take a look at it, at a relatively modest increase in weight and with relatively small changes in performance, we could have brought it up to that standard. So one way to look at this car is it's an experimental that proved what can be done. The other thing is, we weren't really getting the benefit of some of the wonderful things the bigger companies are doing with drivetrain efficiency because we just didn't have the resources. We were using a modified Yamaha motorcycle engine. So there's another 10 to 15% available from what if a large auto company were to simply build an engine the right size for this kind of platform using the technology they're already using, there's probably another 10 or 15% in it that we just didn't have available to us in the resources. This was a very quick project. It was less than 20 months from when I got the call from Oliver Kuttner, who is the team principal, saying, I'm going for the X Prize. Ron says you're the guy to design the body for me, to when Peter Diamandis handed him a check for $5 million for winning it.
Did it cover the cost?
Say again?
The check, did it cover the cost?
Yes. My understanding, because I was fortunately not involved with the finances, is first and most important thing, I got paid. And Ron had agreed to what he would pay certain of us if we won. And I got paid. I got paid that. And the investors got their money back at least. And there was enough to operate the company for several years afterward. Now, it did fade away. I'm not sure about the reasons in detail, whether the demand wasn't there, whether Oliver just didn't have the right business model. The car itself is now in the Henry Ford Museum. Well, we built 4 of them, but one of them is in the Henry Ford Museum at Dearborn. And one of the things actually that I find personally very cool, I originally designed the concept with a pencil on a quad-ruled pad while sitting in a coffee house waiting for my children to finish their martial arts class. It's amazing how much good design work gets done by a combination of understanding and sketching. That's part of my process anyway. That may be generational, but it turns out that after we won, I found the original sketches. I still had them in my clipboard. So I donated them to the museum. And they're now on display with the car to kind of as an illustration of what design is all about. And once again, what's fascinating if you look at it from the context of this talk is you look at that first sketch. I had about 4 different concepts, some of which were really radical. You think this was radical. I had one concept that was a catamaran. It was 2 bullet-shaped bodies with tandem cockpits. So 2 people in each body and wheels. So it was basically 2 motorcycles connected by 2 popsicle sticks. Okay, well, we looked at that and said, okay, that's a little too far out. Now, as a parent, I kind of like that idea. Me and Mama over here, put the kids in the other cockpit. You guys fight. I don't want to hear it. We're good. As long as I can control the door from my side. But if you look at it, there are several radical concepts, and then there's this one, which is the car we actually built. And some of the details are different, but only a little bit. So what it meant is that was the point at which I had really worked out the fundamental architecture. And one of the points I hope you all got from me talking this long is that getting that fundamental architecture of your system right at the beginning is absolutely critical to success. And so that was a few weeks after Ron and I had been talking about what was important. And I came up with this basic architecture and said, I think this will work. And then from that one pencil sketch, if I look at everything from there to the winning car, it was all details. Now, there was an amazing amount of effort that went into those details, a huge amount of work to get those details working right. but the fundamental success of the car was set with that initial pencil sketch from the understanding of what we were trying to do. And I think that's a real important takeaway from this.
But why aren't we seeing?
Yes, sir. Well,
No, I was just going to ask you, because you talked about the importance of having understanding the history of design
yes.
and where ideas come from. And since you're a faculty member, is that something that you actually try to teach, implement in courses? Is there history of ideas?
I try to. I mean, I am unfortunately not a full-time professor. I am still working at Northrop and teaching as a guest lecturer and so forth. But yes, it is something I try to impart to my students all the time. And what was very interesting when we were doing the car is because Ron was a student of race car design and I was an enthusiast back when I was younger. I'm still a race fan. We had this design language that was beautiful because we had all these historical references. So for example, there was an experimental land speed record car called the Stutz Blackhawk that was done in the late 1920s or early 1930s that came very close to breaking the land speed record with an engine that was about 20% of the size of the engine of the car that held it. And had there not been a blowout, a tire blowout leading to a fatal accident on the second run, it would in fact have succeeded. And basically I cribbed shamelessly the architecture of the Stutz Blackhawk. So when Ron and I were talking about it, I didn't have to explain the car in detail to him. I was able to say, I think we need to do something like a Stutz Blackhawk. And his response was, yes, I get it. Let's do that. You know, and then actually the other one was the steel tube chassis, and I don't know whether you guys know, there's this crazy sports car called the Ariel Atom, which is an open frame. Okay. So, you know, I said something like a Stutz Blackhawk, and Ron was talking about a steel tube frame. And so I said, okay, so what we really need here is Buck Rogers builds the Ariel Atom. You know, and that captured the essence of the design right there in one statement. But because we both had this, and he was also a pilot, so he had some knowledge of aircraft, and we had this overlapping historical knowledge that created a design language that really helped because we could reference things from history. But it's very easy to believe that all the valid stuff that was done recently. And it's a mistake. If you go back in history, there's some... What's particularly interesting to me is if you go back to a time in history when some of the underlying technologies were relatively primitive, you see designers having to do really good jobs on the fundamentals because they didn't have the things that let us brute force it. I mean, it's one thing to see a beautifully light structure made out of carbon fiber. But, for example, the Shuttleworth collection in England has some of the most amazing antique airplanes. And one of them is an airplane that was built for a competition. It's called the Wren, the English Electric Wren. And it's a beautiful, long, slender wings. It's a wood airplane covered with fabric. And that airplane is so efficient it can fly on 3.5 horsepower. Just barely. But it can actually take a small human being up into the sky and fly around on 3.5 horsepower.
That's less than 3 kilowatts.
Yeah.
Yes, with a wooden structure covered with linen fabric. And if you look at the detailed design on that airplane, you look at the way they saved weight, it's brilliant. And then you look at the basic shape of the airplane, and you realize that even back then, whoever designed that airplane understood aerodynamic efficiency at its fundamental level. They didn't have the airfoils we have now. They didn't have the materials we have now. They didn't have computational fluid dynamics. He didn't even have access to a wind tunnel. But the point is, if you look at an era where people had to use fundamental understanding to overcome lacks of technology, you find some really clever solutions to things. And in some respects, you find bits of design that really illustrate the important bits of these design drivers. And you can learn a lot from those. Yeah.
Where do you mostly find ideas? Is it in museums?
Where do I mostly find ideas? Museums. I read everything. I look at everything. I mean, my ex-wife once told me that I was the only person she knew who could relate Jell-O to aircraft design. Because one day at dinner I was looking at the slightly aged gelatin dessert, And that got me thinking about how did I make a slightly soft composite skin so I could make a light composite skin that didn't crack. You know, she's just looking at me like, oh God, what did I marry? So, you know, I'm one of those people who's just interested in all kinds of things, and a good designer is, because it's not just in your specialty. You know, I do airplanes. Somebody does something interesting in cars, boats. I see some cool little consumer toy. A lot of what happens is if I see something, some new bit of tech that comes along, some new material, something in the sporting goods store for that matter, I'm always thinking, what can I make out of that? Not what can I do if I just buy that thing, but what can I use it for other than what it's originally created. So it's a, you know, good design is a strange combination of really being technologically rigorous and hacking everything in sight. Yeah.
You mentioned when you were talking about the 3D system to the Airbus that you can't always just hit things with a bigger hammer and more differential equations.
Yes.
Do you restrict yourself from using these advanced methods?
No, absolutely not. I do not restrict myself from using advanced methods. However, what I will not do is use them as a substitute for understanding. So if you take a look at it, a lot of these advanced methods, first of all, they're a brilliant amplifier of human insight. Because when it comes to analysis, if I create a shape, for example, I can analyze the aerodynamics of that shape in 1% of the time it took when I started my career. And that was 1% of what it took 20 years previous to that. Just to give you an example, there's one, just to show you just a simple thing, right? How processors have gotten better. When I started doing computational aerodynamics, so we're talking about 1981-ish time frame, early Jurassic for you, but there was a code we used to analyze wings flying at airliner-like speeds. And we were running it on an IBM mainframe, and a single case took about 4 hours to run. So the way we would do it is we would come in the morning, submit a case, get our results, do some analysis on what is it telling me, make a tweak to the design, submit that run before lunch so that we could get the results in time to do one more tweak for the overnight run. So in 24 hours, I got 3 cycles. That same code hosted on a relatively cheap PC on my desk will run that same case in about 10 seconds. So how many more cycles can I do? Right? But really, I think a lot of it is what you use the design insight for. First of all, there are methods that you can use to explore a design space and really see what those sensitivities are, which helps you understand what the critical variables are. Then you can start being very purposeful. And so then when you get into submitting cases to the advanced method, you know how to talk to it. Because one of the real pitfalls of some of these allegedly advanced methods is they're not necessarily advanced, they're just complicated. And so when you start looking at, for example, optimizers, particularly multidisciplinary optimizers, how you pose the problem to the method very often has the seeds of the answer built into it, and it may not be obvious. How you create your constraint function, for example. And it will do exactly what you told it to do. It just may not be what you think you told it to do. And so this is also where having the insight level understanding is really important, so that when you get those results, you can understand what they mean and if they're valid. But no, I mean, advanced methods, anything that lets you do more and explore deeper, used properly, is enormously powerful.
But not a substitute for understanding.
Oh, absolutely. There is no substitute for good understanding. I mean, otherwise it's kind of like giving a 3-year-old a chainsaw and telling him you need firewood. It's messy. You know, and I don't think we'll ever get to the point where the methodology is so good that you will get as good an answer with a unknowledgeable person operating the method as with a knowledgeable person. Now, I do think that because of the extra insight you can get from it and the extra computing time and all of that, that you take a knowledgeable person with an advanced method, they will end up with a potentially better answer than a knowledgeable person working with more primitive methods, just because it allows that person to do more and use their insight more. So, you know, tools and craftsmen, you need them both. Anyone else? Thank you very much. I've enjoyed it. I hope you have.